Swayam Prabha. Digital India. Educated India.
So, the probability of success is at least 1 by log n. Next we can proceed to the next result, the running time of the algorithm. Okay. Algorithm fast min cut runs in order of n square log n time and order of n square space. Now, you can do this analysis computational complexity part. Are you familiar with recurrence relations? Okay. For recursive functions you can write algorithms, you can write recurrence relations for the computational complexity. Can you try to write the recurrence relation for T of n? You assume that T of n is the computational complexity of finding a min cut in a n node graph. You try? Anyone? T of n equal to? How many recursive calls? 2 recursive calls to produce h1 and h2, correct? What about the size of the argument? N by root 2. So, T of n equal to 2 times T of n by root 2 plus the time needed for the contract algorithm, correct? It is order of n square, that is all, very good. So, you can write the recurrence relation as T of n equal to 2 into T of n by root 2 plus order of n square. What is the base case? T of 1, a constant time, correct? When the size of the number of vertices in the graph is 1, it is going to be a constant. So, T of 1 equal to 1. Now, you can make use of Master's theorem to solve this recurrence, correct? So, I will project the Master theorem. This is a simplified version of the Master theorem. I am not giving the general version. Easily you can read this one, understand and do. Now, see, you are having T of n equal to 2 into T of n by root 2 plus f of n is order of n square. So, it is some c into n square, correct? You want me to write what is the value of a in your recurrence, what is the value of b, then you can do it. And order of n square log n, good. Now, the algorithm needs only order of n square space, okay? That is another beauty of this algorithm, it needs only order of n square space. How do you do this analysis part and show that it needs only order of n square space? Now, when you consider the algorithm, it starts with the root node computation tree and n node graph, then it produces here h1 roughly n by root 2 nodes, h2 roughly n by root 2 nodes, etc., correct? So, at any time when you consider recursion, how many graphs you have to store? I will repeat the question. At any time, see, when you proceed like this level, correct, you consider one particular level, correct? In that level, how many graphs you have to store? See, in the first level, I am 0th level, I am starting with the initial graph, I have to store, then I am producing 2, correct? Then when I produce it with this, it is enough to store this h1 and then proceed, correct? So, it is enough to store 1 graph. At a particular level, at any time, it is enough to store 1 graph, okay? So, at the ith level, number of nodes will be, can you tell me? Here it is n by root 2, the next level it is going to be n by 2, correct, like this. So, at the ith level, n by root 2 power I or 2 power I by 2, correct, okay. Now, to store a graph with n nodes, what is the memory requirement? Assume that you are using the data structure as adjacency matrix, order of n square, correct. So, space requirement at the ith level is order of, so I will write this value exactly and then order of n square by 2 power I, okay. Just square this one. Then you can do the summation over all the levels for the entire memory requirement and produce the correct answer. So, space requirement sigma I varies from 0 to order of log n, height of the tree is log n only, correct. So, I can write order of log n square by, it is order of n square by 2 power I, okay. So, when you do the summation, it is, I will, one minute. So, when you expand this one, it is order of n square into up to order of log n you will be having. So, you can make one more assumption, it is less than or equal to that infinite series summation sigma I equal to 0 to infinity order of n square by 2 power I. Easily you can finish it off. You need only the upper bound. So, less than or equal to order of n square into this series is 1 plus 1 by 2, I think all of you know this one. So, less than or equal to order of n square 1 minus 1 by 2 the whole power minus 1. So, it is order of n square, okay. A beautiful algorithm, correct. So, even to input the graph you need using adjacency matrix order of n square space, that same space itself you can complete the process, okay. How many times you have to repeat, at least how many times I have to repeat the algorithm to get a better probability bound. Yesterday also we discussed that one. There the success probability is greater than or equal to 2 by n square means we will be repeating it n square by 2 times, okay. That itself again a tutorial problem. How do you come to the conclusion that at least you have to repeat it by n square by 2 times. Even you can repeat the algorithm more than n square by 2 times, what happens is the probability of success will be improved. You can boost the probability of success by repeatedly running the algorithm. Now, the probability of success is at least 1 by log n. So, I have to run the algorithm log n times repeatedly. So, the algorithm is repeated log n times, the total complexity is order of n square log square n. Now, can you compare Kargas-Menkat algorithm and the improved version? The probability of success as well as the computational complexity, if you compare, the probability of success is 2 by n square, there at least 2 by n square, here it is at least 1 by log n, okay. Log n is a slowly growing function, okay. So, the probability value is not going to decrease very fastly, but n square compared to log n, it is growing soon. The probability of success will be decreasing in that Kargas-Menkat algorithm, correct, when n grows. Now, the next part is the computational complexity. It was order of n power 4 for Kargas-Menkat algorithm and it is order of n square log square n for this improved version, okay. Now, are you able to appreciate the algorithm? Yes or no? Okay. You really like it? Can you go and implement the algorithm? You try to implement the algorithm, okay. Already I have mentioned about the linear concurrential generator to generate some random numbers. So, try to implement the algorithm, you will really enjoy the beauty of this algorithm, okay. Now, some questions, okay. Based on this discussion, some questions. What is the largest number of min cuts in a graph with n vertices? You assume that there are k distinct min cuts. Okay. Now you know that using the probability analysis, probability of getting a min cut is greater than or equal to 2 by n into n minus 1, which you can write it as 1 by nc2, n choose over 2. Okay. Now, see what about these probabilities, the events, probability of producing one min cut, probability of producing the another min cut, etc. They are disjoint events. Okay. So, the summation of probability of producing sigma I equal to 1 to k min cuts is 1. Okay. So, it is k into 1 by nc2. So, is 1. It is at most 1 you can have. Okay, maximum. Always it need not be actually exactly k value. Now, so what is k is less than or equal to nc2, which is order of n square. Now, can you recollect the number of leaves in that computation tree? It is order of n square. Each leaf corresponds to a min cut, correct? So, in that improved Kargas algorithm, the each leaf corresponds to a min cut, and we are able to show that maximum number of min cuts in the graph is order of n square. So, we are not going to miss out any of the min cuts there. The algorithm will choose one correct min cut among these min cuts and produce the correct output. Okay. NC2. Now, this one you have to complete. To achieve the error probability as order of 1 by n in the fast min cut algorithm, how many times the algorithm have to be repeated? Sorry, the fast min cut is missing here. I will repeat the problem. To achieve the error probability as order of 1 by n, how many times the algorithm have to be repeated? I will give you a hint. Again it should be in terms of your t of n as well as p of n, then you can get the answer. Okay. One more, this is the answer, but you can try to get it. Okay. The last question, see in Kargas min cut as well as the improved algorithm, we contract the edges. Now, see, you do not want to contract an edge, arbitrarily select an edge and contract it. Randomly you choose two vertices of the graph and merge the two vertices. Okay. If you do it like this, is the algorithm is better than the edge contraction algorithm. I will repeat, the contraction is not by choosing randomly one edge, but randomly you select two vertices and merge the two vertices, correct? Is this algorithm better than the edge contraction algorithm? You think it over. When you choose two vertices randomly, there may be an edge between them or may not be an edge. Okay. So, if you feel that this algorithm is not going to be better than the edge contraction algorithm, it is enough to provide one counter example, one graph in which actually when you use this algorithm, the probability of success is very small. I am giving all hints, you please go and try to complete these problems. Okay. So, the hint is actually the graph could be a click with n by root 2 vertices and another click with n by root 2 vertices and only one edge connecting the two clicks. Okay. One click with n by root 2 vertices, that is seal of n by root 2, another one is a click with floor of n by root 2 vertices and one edge connecting two vertices of the clicks. Okay. If you take this graph and proceed, you can prove that the probability of getting a correct min cut or probability of success is exponentially small. Okay. You please try to complete these two as homework. Okay. Now, I would like to summarize this. So, I have introduced randomized algorithms part, and we have discussed Kargar's min cut algorithm and the probability of success analysis. And since we are not happy with the probability of success, we have discussed the improved or modified min cut algorithm, and it is really fantastic compared to the Kargar's min cut algorithm. Okay. See, this paves a lot of actually openings. You can try to improve these algorithms, you try to devise some algorithm and prove that in order of m time you can produce a correct output, whether it is possible or not. Okay. Lot of open problems are there. So, in the next session I am planning to discuss some applications of min cut problem. So, you have already learned ST min cut, correct, and this global min cut, some applications of this min cut problem and some open problems also in the next session. This could be the intro part of my next session. Can you give me some simple applications of this min cut problem? You imagine a communication network, correct? See, suppose there is a bridge in the communication network. All of you know what is a bridge, correct? Is it a reliable network? If that link alone fails, makes the network to fail, correct? One link failure is making the network to fail, so it is not actually a reliable network. Okay. So, how do you get min cut idea there? If you have small size min cuts there, correct, failure of very small number of edges can make the network to fail. So, you can find the min cuts, even not only in one place, you can find all the min cuts, correct, and analyze that one. So, the size of the min cut is playing an important role, and the number of min cut is also playing an important role in the vulnerability analysis of the network. I am not talking about the security aspects of this network, but the reliability part. Okay. So, that is a very simple example of min cut where you apply this min cut idea. Okay. Try to get some more examples so that we can have a discussion. You can be very happy. In the tomorrow's lecture, there is no probability analysis. Only I will be discussing some applications of min cut. Okay. How the application part is converted as a graph model and where min cut plays a role. Okay. So, if there is any other question, I am ready to respond. If not, I would like to complete my lecture. Okay, thank you so much. So, in the next session, we can see the applications.